There is a star in our galaxy right now that is so large, if you could replace our sun with it, you wouldn't know what happened. Not at first. You'd look up, and the sky would still be there. Day would still turn to night. The moon would still rise. But something would be wrong. The sunrises would become slower, the light redder. And within days, you'd realize the sun never fully sets anymore. A crimson glow would begin spreading across the horizon, growing wider each day, until it consumed the entire sky. You would watch, helpless, as this red wall expanded overhead, swallowing star after star, erasing the night itself. And then you'd understand. You're not looking at a sun anymore. You're inside one. The Earth, Mars, the asteroid belt, everything out to Saturn's orbit. All of it would be buried beneath the surface of this single object. This isn't a thought experiment. This isn't exaggeration. Stephenson 2.18 exists right now, 19,000 light years away. A sphere of plasma so incomprehensibly vast that our entire conception of large becomes meaningless in its presence, and it sits at the absolute edge of what physics will permit, one step larger, and it would tear itself apart. This is the story of that star, and what it means to exist at the boundary where the universe itself says no further. If this journey interests you, consider subscribing. To understand what makes Stephenson 2.18 so extraordinary, we first need to recalibrate our sense of scale entirely. We need to abandon the human perspective, the terrestrial perspective, even the solar system perspective, and enter a realm where the measurements themselves become abstract, where numbers stop meaning what they normally mean, where even the speed of light becomes a useful ruler for describing the diameter of a single object. This is not easy. Our brains did not evolve to comprehend these scales. We evolved to understand the size of a predator, the distance to water, the height of a tree. We can stretch our imagination to grasp the size of our planet, perhaps even the distance to the moon. But when we venture into the realm of the truly large stars, we are asking our minds to do something they were never designed to do. The sun, our familiar star, the object that makes life on Earth possible, has a diameter of about 1.4 million kilometers. That is already difficult to visualize. If Earth were the size of a marble, the sun would be a sphere roughly 1.5 meters across. But even this comparison fails, because we cannot truly hold 1.5 meters of flaming plasma in our minds. We need better anchors. Light, which crosses the distance from Earth to the moon in just over a second, takes about 4.6 seconds to travel from one side of the sun to the other. The sun is big enough that light, the fastest thing in the universe, needs nearly 5 seconds to traverse it. That gives us a slightly better sense of scale, though it still feels abstract. Now consider this. Stephenson 2.18 has a radius approximately 2,000 times larger than the sun. Not twice as large, not 20 times, 2,000 times. If the sun's light takes about 2.3 seconds to reach from its center to its surface, light from the center of Stephenson 2.18 would take roughly 76 minutes to reach its surface. More than an hour. Think about that. Light leaves the core of this star and spends over an hour just traveling through the star itself before it finally escapes into space. The star is so large that it contains within itself a light hour of distance. When we talk about interplanetary distances, we often use light minutes and light hours. Earth is about 8 light minutes from the sun. Jupiter is about 43 light minutes away. Stephenson 2.18 is so enormous that the distance from its center to its edge is comparable to the distance from the sun to a point well beyond the orbit of Mars. But what does it mean to say a star is the largest? This is where we need to be precise, because in astronomy, size can mean different things depending on what you are measuring. When we talk about the largest star, we are almost always talking about radius or diameter, the physical extent of the star's visible surface. But stars also have mass, and mass does not always correlate with size in the way you might expect. There are stars with enormous mass compressed into relatively small volumes, and there are stars with relatively modest mass bloated to staggering sizes. Stephenson 2.18 falls into the latter category. It is a red supergiant, a star in the late stages of its life, and like all red supergiants, it has swollen to grotesque proportions as it nears the end of its existence. To understand why this matters, think about density. The sun has an average density of about 1.4 grams per cubic centimeter, roughly 1.4 times the density of water. It is not uniform, of course. The core is incredibly dense, while the outer layers are more tenuous, but on average, the Sun is somewhat denser than water. Now consider Stephenson 218. Despite being 2,000 times larger in radius, it is only about 12 to 15 times more massive than the Sun. This means its average density is astonishingly low. If you could somehow take a cubic meter of material from the outer layers of Stephenson 218, it would contain far fewer atoms than a cubic meter of Earth's atmosphere at sea level. In fact, the outer regions of this star are so diffuse that they barely qualify as matter in the conventional sense. They are more like a hot, glowing fog, a plasma so thin that it would be considered a near-perfect vacuum by terrestrial standards. This is one of the most counterintuitive aspects of the largest stars. They are not the most massive stars. The most massive stars are typically much smaller and far denser. A star like R136A1, one of the most massive stars known, has a mass perhaps 300 times that of the Sun, but its radius is only about 30 to 40 times larger. It is a compact, ferociously hot blue giant, burning through its fuel at an insane rate. Stephenson 218, by contrast, is a lumbering giant, a dying star that has expanded to fill a volume of space that defies comprehension, even as its mass remains relatively modest by stellar standards. So when we say Stephenson 218 is the largest star, we mean it occupies the most space. If you were to construct a sphere with the same radius as this star, the volume inside would be truly staggering. Volume scales with the cube of the radius, which means that if Stephenson 218 is 2,000 times larger in radius than the Sun, its volume is approximately 8 billion times greater. 8 billion. If you could somehow fill this star with suns, you could fit 8 billion of them inside. The human mind simply does not have the architecture to process this number in a meaningful way. 8 billion is the approximate population of Earth. Imagine every person on Earth, and then imagine that each person represents an entire sun, and all of those suns fit inside a single star. And that star is real. It exists. It is out there right now, shining in the darkness. The discovery of stars like Stephenson 218 is a relatively recent achievement in the history of astronomy. For most of human history, we had no idea that stars came in different sizes at all. Ancient astronomers thought stars were fixed points of light, perhaps small fires or holes in the celestial sphere through which divine light shone. Even after the invention of the telescope, it took centuries to understand that stars were distant suns, each with its own characteristics. The realization that some stars were vastly larger than others came only in the 20th century, as spectroscopy and other techniques allowed astronomers to determine the temperatures, luminosities, and distances of stars with increasing precision. Stephenson 218 is located in the Stephenson 2 cluster, a massive open cluster situated about 19,000 light-years from Earth, near the galactic plane in the constellation Scutum. The cluster itself is extraordinary, containing some of the largest and most luminous stars known. It is a young cluster, perhaps only 14 to 20 million years old, which in cosmic terms is barely an instant. The stars within it are predominantly red supergiants, massive stars that have evolved rapidly and are now in the final stages of their lives. The cluster is heavily obscured by interstellar dust, which makes it difficult to observe in visible light. For a long time, clusters like Stephenson 2 were hidden from view, their secrets locked away behind veils of cosmic dust that absorb and scatter light. It was only with the advent of infrared astronomy that we could peer through this dust and see what lay beyond. Infrared light has longer wavelengths than visible light, which allows it to pass through dust clouds that would completely block shorter wavelengths. In the late 20th and early 21st centuries, infrared surveys of the sky began to reveal clusters of massive stars that had been invisible to previous generations of astronomers. Stephenson 2 was one of these discoveries, and as astronomers studied the stars within it, they realized they were looking at some of the most extreme objects in the galaxy. Measuring the size of a star like Stephenson 218 is an extraordinarily difficult task. The star is so far away that even through the most powerful telescopes, it appears as little more than a point of light. You cannot simply look at it and measure its diameter the way you might measure the diameter of a planet in our solar system. Instead, astronomers must use indirect methods, combining observations across multiple wavelengths with theoretical models of stellar structure and evolution. The first step is to determine the star's distance. This is crucial because without knowing how far away the star is, you cannot determine its true brightness or size. For nearby stars, astronomers use a technique called parallax, which involves measuring the apparent shift in a star's position as Earth orbits the Sun. But for stars as distant as Stephenson 218, parallax becomes impractical because the shifts are too small to measure accurately. Instead, astronomers rely on other methods. One approach is to study the cluster as a whole, using the properties of its member stars to estimate the distance. By analyzing the colors and brightnesses of many stars in the cluster and comparing them to theoretical models, astronomers can infer how far away the cluster must be. Once the distance is known, the next step is to determine the star's luminosity, the total amount of energy it emits per second. This is done by measuring the star's apparent brightness as seen from Earth, and then correcting for the distance and any interstellar dust that might be dimming the light. For a star like Stephenson 218, this correction is substantial because the cluster is embedded in a dusty region of the galaxy. Infrared observations are particularly useful here because they are less affected by dust. With the luminosity in hand, astronomers can then use theoretical models to estimate the star's radius. A star's luminosity depends on both its surface temperature and its surface area. The relationship is described by the Stefan-Boltzmann law, which states that the luminosity of a star is proportional to its surface area multiplied by the fourth power of its temperature. Red supergiants like Stephenson 218 have relatively cool surfaces, with temperatures around 3000 to 4000 Kelvin, compared to the Sun's surface temperature of about 700 Kelvin. Because they are so cool, their luminosity per unit area is relatively low. To be as luminous as they must have enormous surface areas, which means enormous radii. The exact radius of Stephenson 218 is still a matter of some debate and uncertainty. Different studies have produced slightly different estimates, depending on the assumptions made in the modeling process and the quality of the observational data. Some estimates place the radius at around 2000 solar radii, while others suggest it could be somewhat smaller or larger. There is also the question of how to define the star's edge. Red supergiants have very diffuse outer atmospheres, and the transition from the star's photosphere to the surrounding interstellar medium is not sharp. The radius typically quoted is the distance from the center of the star to the photosphere, the layer from which most of the light we see is emitted. But the star's atmosphere extends well beyond this, creating a vast halo of tenuous gas that gradually fades into space. Despite these uncertainties, one thing is clear. Stephenson 218 is among the very largest stars ever discovered, and it may indeed be the largest, depending on how we measure and what other candidates we consider. There are other contenders, of course. Uy-Scuti, another red supergiant, held the title of largest known star for several years, though more recent measurements have suggested it may be somewhat smaller than previously thought. VY Canis Majoris, once thought to be the largest, has also been revised downward. The truth is that measuring these extreme stars is so difficult that the rankings can shift as new data becomes available and models improve. But regardless of which star holds the current record, Stephenson 218 is undeniably one of the titans of the galaxy, a star so large that it pushes against the very limits of what is physically possible. To truly grasp the scale of this star, let us perform a thought experiment. Imagine that we could somehow remove our Sun from the center of the solar system and replace it with Stephenson 218. What would happen? The first thing to understand is that the star would not fit, not even close. The Sun sits at the center of our solar system, with Mercury orbiting at a distance of about 58 million kilometers, Venus at 108 million kilometers, Earth at 150 million kilometers, and Mars at about 228 million kilometers. These are the inner rocky planets, the worlds that orbit relatively close to the Sun. Now, if Stephenson 218 has a radius of roughly 2000 solar radii, its radius would be approximately 1.4 billion kilometers. To put that in perspective, Earth orbits the Sun at a distance of 150 million kilometers, which is 1 astronomical unit. Stephenson 218 would have a radius of about 9 to 10 astronomical units. This means its surface would extend far beyond the orbit of Mars, past the asteroid belt, and approach the orbit of Jupiter, which sits at about 5.2 astronomical units from the Sun. In fact, depending on the exact size of the star, its surface might even reach or surpass Jupiter's orbit. Think about what this means. Mercury, Venus, Earth, and Mars would all be inside the star, not orbiting it. Inside it, they would be engulfed by the star's outer atmosphere, plowing through plasma that, while incredibly diffuse, would still exert drag on the planets and cause them to spiral inward. Over time, they would be consumed, vaporized as they descended into deeper, hotter layers of the star. Jupiter, the giant of our solar system, would find itself either just barely outside the star's photosphere or skimming its outermost layers, depending on the star's exact radius. Saturn, at about 9.5 astronomical units, would be in a precarious position, orbiting just beyond the star's visible edge, but still immersed in its extended atmosphere and subjected to intense radiation. From Earth, if it somehow survived, the sky would be filled entirely by the star's surface. You would not see a sun in the sky. You would see an endless red glow in every direction, because you would be inside the star. The concept of day and night would cease to exist. There would be no darkness, only the dim, pervasive red light of the star's cool photosphere surrounding you on all sides. The temperature would be unbearable, though perhaps not as high as you might expect. The outer layers of a red supergiant are cool by stellar standards, but still hot enough to vaporize any planet or object that found itself within them. This thought experiment reveals something profound about the scale we are dealing with. We are used to thinking of the solar system as vast, an expanse of empty space punctuated by planets separated by enormous distances. But Stephenson 218 is so large that it trivializes these distances. It would swallow the inner solar system whole and reach out to threaten even the outer planets. It is a single object, a single star, that occupies a volume of space we normally think of as containing an entire planetary system. But why does a star become this large? What physical processes allow a star to swell to such extraordinary proportions? And why do not all stars do the same? The answer lies in the life cycle of stars and the delicate balance between gravity and radiation pressure that governs their structure. Stars form from clouds of gas and dust that collapse under their own gravity. As the cloud collapses, it heats up, and eventually the core becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy in the process. This energy creates an outward pressure that pushes against the inward pull of gravity, and the star reaches a stable equilibrium. For most of a star's life, it exists in this stable state, burning hydrogen in its core and maintaining a relatively constant size. But this equilibrium depends on the star's mass. More massive stars burn hotter and brighter, and they exhaust their fuel much more quickly than less massive stars. The Sun, a relatively modest star, will spend about 10 billion years on the main sequence, the stable phase of its life. It has been burning for about 4.6 billion years and has roughly another 5 billion years to go. But a star with 10 times the Sun's mass will burn through its hydrogen fuel in just 20 million years. A star with 20 or 30 solar masses might last only a few million years. Stephenson 218, with an estimated initial mass of perhaps 20 solar masses or more, is one of these short-lived giants. When a massive star exhausts the hydrogen in its core, it does not simply die. Instead, it begins to fuse heavier elements. The core contracts and heats up, and hydrogen fusion continues in a shell surrounding the core while helium begins to fuse in the core itself. This process releases even more energy, and the star's outer layers expand dramatically. The star becomes a red giant, or if it is massive enough, a red supergiant. The surface moves farther and farther from the core, cooling as it does so. The star becomes redder and vastly larger, even as the core continues to contract and heat up. As the core continues to fuse heavier and heavier elements, carbon, oxygen, neon, silicon, the star's structure becomes increasingly complex. It develops an onion-like layered structure, with different elements fusing in different shells at different depths. The core becomes denser and hotter with each stage, while the outer envelope continues to expand. For the most massive stars, This process can lead to radii of hundreds or even thousands of times the original main sequence size. Stephenson 218 is in this late stage of evolution. It has likely already fused hydrogen and helium in its core, and may be fusing even heavier elements. Its core is probably no larger than Earth, compressed to incredible densities, while its outer envelope has expanded to a size that dwarfs the entire inner solar system. The contrast is almost absurd. At the center of this vast, bloated star is a core smaller than our planet, but so dense and hot that it contains the mass of many suns and produces energy at a rate that would incinerate anything that came near it. And surrounding this tiny, ferocious core is a diffuse atmosphere thousands of times larger than the original star, a gossamer shell of glowing gas held together by gravity so tenuously that it seems almost miraculous that it exists at all. But there are limits to how large a star can grow, and those limits are set by the fundamental physics of stellar structure. As a star expands, its surface moves farther from the core, and the gravitational pull at the surface decreases. Gravity falls off with the square of the distance, so if the radius of a star increases by a factor of 2,000, the surface gravity decreases by a factor of 4 million. At the surface of Stephenson 218, the gravitational pull is almost negligible, far weaker than the gravity you feel standing on Earth. In fact, the surface gravity of a star like this is so weak that the star's own radiation pressure can begin to overcome it. Every photon of light carries momentum, and when photons are absorbed or scattered by atoms in the star's atmosphere, they transfer that momentum, creating an outward force. In a normal star like the Sun, this radiation pressure is significant, but it is still much weaker than gravity. However, in a bloated red supergiant with extremely low surface gravity, radiation pressure becomes a major player. The star is so luminous, producing so many photons, that the outward push from radiation can rival or even exceed the inward pull of gravity at the surface. This creates a precarious situation. The star is teetering on the edge of stability. If the radiation pressure becomes too strong, it can lift material off the star's surface and blow it away into space. This process, known as a stellar wind, is common in massive stars, but in red supergiants like Stephenson 218, it becomes extreme. These stars are constantly shedding mass, losing material from their outer layers at a prodigious rate. The stellar wind from a red supergiant can carry away the equivalent of Earth's mass every few thousand years. Over the star's lifetime, it can lose a significant fraction of its original mass, creating a vast shroud of gas and dust surrounding the star. This mass loss is one of the key factors that limits how large a star can become. As the star sheds its outer layers, it loses mass, and the reduced mass means the star's gravity weakens even further. Eventually, the star reaches a point where it cannot hold itself together. The outer layers become so loosely bound that they are no longer part of the star in any meaningful sense. They drift away into space, forming a nebula that will eventually disperse into the interstellar medium. There is another limit as well, one set by the sheer luminosity of the star. The most luminous stars in the universe are close to what is known as the Eddington limit, the point at which the outward radiation pressure exactly balances the inward pull of gravity. If a star exceeds the Eddington limit, radiation pressure dominates, and the star begins to blow itself apart. For a given mass, there is a maximum luminosity the star can have before this happens. Red supergiants like Stephenson 218 are not close to this limit in their cores, but in the outer layers, where the density is extremely low. Local regions of the atmosphere can experience radiation pressure that approaches or exceeds what gravity can hold in place. This leads to instabilities, pulsations, and episodic mass ejections. These stars are not static objects. They are dynamic, chaotic, and unstable. Observations of red supergiants have shown that they vary in brightness over time, sometimes quite dramatically. These variations are thought to be caused by pulsations, oscillations in the star's radius as the outer layers expand and contract. The star is so large and so diffuse that sound waves and shock waves can propagate through the atmosphere, causing the star to swell and shrink like a beating heart. During these pulsations, the star can temporarily become even larger, or it can shed additional mass as the shock waves lift material off the surface. The combination of low surface gravity, intense radiation pressure, and pulsations means that stars like Stephenson 218 are living on borrowed time. They are unstable giants, held together by the most tenuous of forces, constantly losing mass and energy to their surroundings. They cannot last long in this state. For a star like Stephenson 218, the time remaining is measured in thousands or perhaps tens of thousands of years, a mere blink of an eye compared to the millions or billions of years that stars spend in more stable phases of their lives. And what happens when this time runs out? The star's fate is sealed by the inexorable progress of fusion in its core. As the core continues to fuse heavier elements, it climbs the periodic table, producing carbon, oxygen, neon, magnesium, silicon, and finally iron. Iron is the end of the line. Fusing iron does not release energy, it consumes energy. When the core becomes predominantly iron, fusion stops. The core can no longer support itself against gravity. In a fraction of a second, it collapses. The collapse is catastrophic. The core, which moments before was the size of Earth, compresses to a sphere perhaps 20 kilometers across, a neutron star or possibly a black hole. The gravitational energy released in this collapse is staggering, equivalent to the energy the Sun will emit over its entire 10 billion year lifetime, but released in a few seconds. This energy drives a shock wave outward through the star, and the star explodes in a supernova, one of the most violent events in the universe. For a brief moment, the supernova can outshine an entire galaxy. The explosion ejects the star's outer layers into space at speeds of thousands of kilometers per second, enriching the interstellar medium with the heavy elements forged in the star's core and in the explosion itself. These elements, carbon, oxygen, silicon, iron, and many others, are the raw materials for new stars, new planets, and eventually new life. Every atom in your body heavier than hydrogen and helium was created in the core of a star or in a supernova explosion. In a very real sense, we are made of stardust, the remnants of stars that lived and died billions of years ago. Stephenson 218 is destined for this fate. It will end its life in a supernova, and when it does, it will briefly become one of the brightest objects in the galaxy. Astronomers will study the explosion, learning about the final moments of the star's life and the physics of supernova. And after the fireworks fade, what remains will be a neutron star or a black hole, surrounded by an expanding cloud of glowing gas, a supernova remnant that will persist for thousands of years before finally dispersing into the vastness of space. But until that moment comes, Stephenson 218 continues to exist, a monument to the extremes of stellar evolution. It is a star that challenges our understanding of what a star can be. It forces us to confront the limits of size, the boundaries set by gravity, radiation, and the laws of physics. And it reminds us that the universe is capable of creating objects so large, so energetic, and so strange that they stretch the limits of our imagination. To put the scale of Stephenson 218 into yet another perspective, consider the speed of light again. Light travels at approximately 300,000 kilometers per second. At this speed, light can circle the Earth more than 7 times in a single second. It can travel from the Earth to the Moon in just over a second. It takes light about 8 minutes to travel from the Sun to the Earth, a distance of 150 million kilometers. These are the scales we use to describe distances in our solar system, and they already feel vast. Now consider a photon of light emitted from the core of Stephenson 218. This photon begins its journey in a region of unimaginable heat and density, where temperatures reach tens of millions of degrees, and the pressure is so intense that atomic nuclei are forced together, fusing and releasing energy. The photon is born in this inferno, a tiny packet of energy created by the fusion of atomic nuclei. But it cannot simply escape. The core of the star is opaque, filled with matter so dense that photons are constantly absorbed and re-emitted by atoms. The photon bounces around, taking a random walk through the star's interior. In a star like the Sun, this journey from core to surface takes thousands of years, even though light itself travels at the ultimate cosmic speed limit. The photon is absorbed and re-emitted so many times, its path so tortuous, that it takes millennia to work its way outward. But once it reaches the surface, it escapes into space and travels in a straight line. From the Sun's surface to Earth takes just 8 minutes. In Stephenson 218, the journey is even more extraordinary. The core is surrounded by layer upon layer of stellar material, each layer adding to the distance the photon must travel. The star's radius is so enormous that even if a photon could somehow travel in a straight line from the center to the surface at the speed of light, it would take over an hour. But of course, it cannot travel in a straight line. It must take that same random walk, bouncing endlessly through the star's interior. By the time a photon created in the core of Stephenson 218 finally escapes into space, the star itself may have changed. The photon carries information about conditions in the core at the moment it was created, but by the time it emerges, thousands or even tens of thousands of years may have passed. This has profound implications for our understanding of stars. When we observe a star like Stephenson 218, we are not seeing it as it is right now. We are seeing light that was emitted from its surface, and that light contains information about the interior of the star, but that information is ancient by human standards. The star we observe is a palimpsest, a layered record of its own past, with light from different depths carrying information from different epochs in the star's evolution. And that is just the light travel time within the star. Stephenson 218 is located about 19,000 light years from Earth. This means the light we see today left the star 19,000 years ago. When that light began its journey, humans on Earth were still in the Stone Age, living as hunter-gatherers, painting on cave walls, and beginning to develop the first rudimentary forms of agriculture. Entire civilizations have risen and fallen in the time it took that light to reach us. The star we see when we point our telescopes at Stephenson 218 is not the star as it exists today. It is the star as it existed 19,000 years ago. For all we know, the star could have already exploded, and the light from that supernova is on its way to us right now, crossing the interstellar void at the speed of light. We would not know until that light arrived. For the next 19,000 years, if the star did explode today, we would continue to see it shining peacefully in the sky, oblivious to its death. This temporal disconnect is one of the eerie aspects of astronomy. We are always looking into the past. Every photon that enters our telescopes is a messenger from history, carrying news of events that happened long ago. The farther away an object is, the older the news. When we observe distant galaxies billions of light years away, we see them as they were billions of years ago, when the universe was young and very different from what it is today. Some of those galaxies may no longer exist. They may have been destroyed in collisions with other galaxies or torn apart by gravitational forces, but we will not see those events for billions of years when the light from them finally reaches us. Stephenson 218, at a mere 19,000 light years, is practically in our cosmic neighborhood, but even at this relatively close distance, we are seeing ancient history. The star we observe is a snapshot from the deep past, a frozen moment in the life of a giant that may or may not still exist. The study of stars like Stephenson 218 also reveals something fundamental about the limits of stellar physics. Stars cannot grow indefinitely. There is a maximum size beyond which a star cannot exist, and that maximum is set by the interplay of gravity, radiation pressure, and the structural properties of stellar matter. As we have discussed, as a star grows larger, its surface gravity decreases. At the same time, its luminosity increases, and with it, the radiation pressure. Eventually, a point is reached where the radiation pressure is strong enough to overcome gravity and drive mass loss at such a high rate that the star cannot maintain its structure. There is also a limit related to the star's mass and density. A star must have enough mass to generate the gravitational pressure needed to initiate and sustain fusion in its core. But if a star is too diffuse, if its outer layers are too spread out, then the density in those layers becomes so low that they are barely bound to the star at all. The star becomes a nebula with a bright core at the center, rather than a cohesive object. At some point, we have to ask whether we are still looking at a star or simply a cloud of gas illuminated by a fusion reactor at its heart. Theoretical models of stellar structure suggest that the maximum radius for a star is somewhere around 2,000 to 3,000 solar radii, depending on the star's mass, composition, and evolutionary state. Stephenson 218 sits right at or near this limit. It is about as large as a star can be before it ceases to be a star in the conventional sense. This makes it not just interesting, but scientifically crucial. By studying this star, we are probing the boundaries of what is possible, testing our models of stellar evolution and structure at their extremes. and the universe has provided us with a natural laboratory for this study. Stephenson 218 is not unique. There are other red supergiants of comparable size, other stars pushing against the same physical limits. Each one is slightly different, with its own mass, composition, and evolutionary history, and each one provides a slightly different test of our theories. By observing a population of these extreme stars, astronomers can refine their models, improve their understanding of stellar physics, and gain insight into the processes that govern the lives and deaths of the most massive stars. One of the challenges in studying these stars is their rarity. Red supergiants are the late evolutionary stages of massive stars, and massive stars are rare to begin with. For every star with a mass of 20 or 30 times the Sun, there are thousands or millions of Sun-like stars. And red supergiants represent only a brief phase in the life of a massive star, lasting perhaps a few 100,000 years out of a total lifetime of a few million years. At any given moment, only a tiny fraction of the massive stars in the galaxy are in the red supergiant phase. This means that even in a galaxy of hundreds of billions of stars, there are only a few thousand red supergiants at most, and only a handful of those are as extreme as Stephenson 218. Finding these red giants requires surveying large areas of the sky, often in infrared wavelengths where they are brightest and where interstellar dust is less of a hindrance. Modern infrared surveys, conducted by telescopes both on the ground and in space, have catalogued millions of stars and identified thousands of red supergiants. Among these, a few dozen stand out as exceptionally large, and Stephenson 218 is among the most extreme. But identifying a candidate is only the first step. Confirming its size requires detailed follow-up observations. Astronomers must measure the star's spectrum, the distribution of light across different wavelengths, to determine its temperature and composition. They must measure its brightness and correct for the dimming effects of interstellar dust. They must estimate the distance to the star, often a difficult and uncertain task, and they must construct a model of the star's structure that is consistent with all the observations. This is a painstaking process that can take years and involves data from multiple telescopes and instruments. Even then, uncertainties remain. The distances to stars like Stephenson 218 are not known with perfect precision. The amount of interstellar dust along the line of sight can be difficult to estimate. The star's temperature and luminosity can vary over time due to pulsations and other instabilities. All of these factors contribute to uncertainty in the derived radius. This is why different studies sometimes produce different values for the size of the same star, and why the title of largest star can shift from one object to another as new data becomes available. Despite these uncertainties, the broad picture is clear. Stephenson 218 is one of the largest stars ever discovered, a red supergiant of truly staggering proportions. It is a star that sits at the edge of what is physically possible, a testament to the power and creativity of the universe in creating objects of extreme scale. Let us return to the question of what would happen if this star replaced our Sun. But this time, let us think about the experience from a more human perspective. Imagine you are an astronaut aboard a spacecraft near Earth, and suddenly, impossibly, our Sun is replaced by Stephenson 218. What would you see? First, you would notice the light. The Sun, from Earth, appears as a blindingly bright disk about half a degree across in the sky. Stephenson 218 at its distance would appear vastly larger. In fact, if it were at the same distance as the Sun, it would fill nearly the entire sky. You would not see a disk, you would see an endless red expanse. It would be as if you were inside a vast sphere of glowing red light. There would be no horizon, no sense of up or down, just the pervasive red glow of the star's surface surrounding you in all directions. But you would not be on Earth for long. The radiation from Stephenson 218, even though it is cooler than the Sun, would be overwhelming. The star's total luminosity is hundreds of thousands of times greater than the Sun's. Even though its surface is cooler, the sheer size means it radiates far more energy overall. Earth, at its current distance of 1 astronomical unit, would be subjected to a radiation flux far greater than it receives from the Sun. The planet's atmosphere would be stripped away almost immediately. The oceans would boil off. The surface would be scorched and vaporized. Within days or weeks, Earth would cease to exist as a planet. It would be reduced to a cloud of vapor, and even that vapor would be blown away by the intense radiation and stellar wind. But of course, this is all moot, because if Stephenson 218 replaced the Sun, Earth would already be inside the star. We discussed this earlier, but let us think about it more carefully. What does it mean to be inside a star? The outer layers of a red supergiant are incredibly diffuse. The density is so low that, by terrestrial standards, it would be considered a vacuum. But it is not empty. It is filled with hot plasma, atoms stripped of their electrons, moving at high speeds. The temperature, even in the outer layers, would be thousands of degrees. Any solid object, like a planet, would be subjected to this heat and would begin to ablate, losing material from its surface. But the main effect would be gravitational. Even though the surface gravity of Stephenson 218 is weak, the gravity at the star's center is not. If Earth were somehow embedded in the outer layers of the star, it would experience a gravitational pull toward the center. It would also experience drag as it moved through the diffuse plasma. Over time, this drag would cause the planet to lose orbital energy and spiral inward. As it descended into deeper layers of the star, the temperature and density would increase. The planet would heat up, its surface would melt, and eventually, it would be torn apart by tidal forces and completely vaporized. The process would not be instantaneous, but it would be inevitable. There is no way for a planet to exist within a star, not for long. The star is simply too hot, too energetic, and too hostile an environment. This thought experiment underscores the alienness of these objects. Stars are not places you can visit. They are not environments where anything familiar can exist. They are furnaces, powered by nuclear fusion, where the conditions are so extreme that matter exists in states completely unlike anything we encounter in everyday life. And red supergiants, despite their relatively cool surfaces, are among the most extreme stars of all, precisely because of their size. Now let us shift our perspective and think about what Stephenson 218 means for our understanding of the universe. This star is not just a curiosity, a record holder in the cosmic book of superlatives. It is a window into the fundamental processes that govern the formation, evolution, and death of stars. By studying stars like this, we learn about the limits of stellar physics, the boundaries beyond which stars cannot exist. One of the key insights is that stars are self-regulating systems. They exist in a delicate balance between the inward pull of gravity and the outward push of radiation pressure. When a star is stable, these forces are in equilibrium, and the star maintains a constant size. But this equilibrium is dynamic, not static. The star is constantly adjusting, responding to changes in its internal structure as it fuses elements in its core. When the core exhausts one type of fuel and begins fusing another, the star's structure changes. The core contracts, the outer layers expand or contract, and the star moves to a new equilibrium. For massive stars, this process is rapid and dramatic. They burn through their fuel quickly, and they pass through multiple stages of fusion in their cores. Each stage lasts a shorter time than the one before. A star might spend millions of years fusing hydrogen, but only hundreds of thousands of years fusing helium, and only thousands of years fusing carbon. By the time it reaches silicon fusion, the process is so fast that the entire silicon burning phase lasts only a few days. The star is racing toward its inevitable collapse and explosion. Red supergiants like Stephenson 218 are in the late stages of this process. They have already fused hydrogen and helium, and they are now fusing heavier elements. The exact stage depends on the star's mass and composition, but it is likely that Stephenson 218 is somewhere in the middle to late stages, perhaps fusing carbon or oxygen, or possibly even further along. The star's enormous size is a consequence of this late stage evolution. As the core contracts and heats up, the outer layers expand, and the star swells to its current immense proportions. But this size comes at a cost. The star is losing mass at a prodigious rate. The stellar wind is so strong that the star is shedding the equivalent of Earth's mass every few thousand years. Over its time as a red supergiant, it may lose a significant fraction of its original mass. This mass loss has important consequences for the star's ultimate fate. A star's final state, whether it becomes a neutron star or a black hole, depends in part on how much mass it has left when it finally explodes. If a red supergiant loses too much mass, it may not have enough left to form a black hole, and it will instead collapse to a neutron star. Conversely, if it retains enough mass, the core collapse will be so energetic that not even a neutron star can form, and a black hole will be the result. This makes the study of mass loss in red supergiants critically important. Astronomers want to understand how much mass these stars lose, how fast they lose it, and what factors control the mass loss rate. Is it primarily driven by radiation pressure, by pulsations, by the star's rotation or magnetic field? These are active areas of research, and observations of stars like Stephenson 218 provide crucial data. One way to study mass loss is to observe the star's circumstellar environment, the region immediately surrounding the star. As the star sheds material, this material does not simply disappear. It forms a shell or cloud around the star, which can be detected by its emission or absorption of light. Infrared observations are particularly useful here because dust grains form in the cooling gas, and these grains absorb light from the star and re-emit it in the infrared. By studying the infrared emission, astronomers can map the distribution of dust and gas around the star and estimate the mass loss rate. For Stephenson 218, observations have revealed a complex circumstellar environment with evidence of extensive mass loss. The star is surrounded by a shroud of material that extends far beyond the photosphere, creating a kind of extended atmosphere or halo. This material is rich in dust, which is why the star is so bright in the infrared. The dust absorbs the star's visible and ultraviolet light and re-emits it at longer wavelengths, making the star appear much brighter in the infrared than it would otherwise. This circumstellar material is also a fossil record of the star's recent history. The material we see around the star today was ejected hundreds or thousands of years ago. By studying the distribution and composition of this material, astronomers can learn about the star's past, about periods of intense mass loss or changes in the star's activity. In some cases, the material shows evidence of asymmetries or clumps, suggesting that the mass loss was not smooth and continuous, but episodic and irregular. This is consistent with the idea that red supergiants undergo violent pulsations and outbursts that eject material in sporadic bursts. These observations paint a picture of a star in turmoil, a giant on the edge of instability, constantly shedding its outer layers as it struggles to maintain its structure against the relentless forces of gravity and radiation. It is not a peaceful existence. The star is engaged in a losing battle, and its eventual defeat is certain. But in the meantime, it shines with a brilliance that belays its precarious state, a beacon of light in the darkness of space. The comparison between Stephenson 218 and other extreme stars also tells us something about the diversity of stellar evolution. Not all massive stars become red supergiants. Some, depending on their initial mass, composition, and other factors, may evolve along different paths. They may become blue supergiants, or luminous blue variables, or Wolf-Rayet stars, each representing a different stage or branch of massive star evolution. The exact path a star follows depends on a complex interplay of factors, and astronomers are still working to understand all the details. Red supergiants represent one particular evolutionary track, one that seems to be favored by stars with certain masses and compositions. These stars have expanded to enormous sizes, and they will eventually explode as supernovae. But not all supernovae are the same. Some are brighter than others, some eject more material, and some leave behind different types of remnants. The properties of the supernova depend on the properties of the star that explodes, and so understanding red supergiants like Stephenson 218 helps us understand supernovae as well. Supernovae are among the most important events in the universe. They are the primary mechanism by which heavy elements are dispersed into the interstellar medium, enriching the gas from which new stars and planets will form. Without supernovae, the universe would be a very different place. There would be no carbon, no oxygen, no iron, none of the elements that make up planets and living organisms. In a very real sense, supernovae are the factories that produce the raw materials for life. Stephenson 218 is destined to become one of these factories. When it explodes, it will eject its outer layers into space at tremendous speeds, creating a shockwave that will plow through the surrounding interstellar medium, heating it and compressing it, and triggering the formation of new stars. The explosion will be visible across the galaxy, a brilliant point of light that will fade over weeks or months. leaving behind a glowing nebula that will persist for thousands of years. Astronomers eagerly await this event, not because they wish for the star's death, but because supernovae are rare and scientifically invaluable. Each supernova provides a wealth of data, a chance to observe the violent death of a star, and to test our theories of stellar evolution and explosion physics. Modern telescopes and instruments are capable of observing supernovae in exquisite detail, capturing spectra at different stages of the explosion, measuring the light curves, and tracking the expansion of the ejected material. All of this data feeds back into our models, helping us refine our understanding of how stars live and die. But we do not know when Stephenson 218 will explode. It could be tomorrow, or it could be 10,000 years from now. The timescales of stellar evolution, even for massive stars in their final stages, are long by human standards. The star might already have exploded, and we are simply waiting for the light to reach us. Or it might continue to shine for millennia to come. We cannot know. All we can do is watch and wait, and study the star while it lasts. This uncertainty is part of what makes astronomy both frustrating and exhilarating. We are observers, not experimenters. We cannot control the objects we study or speed up their evolution to see what happens next. We must take what the universe gives us, and we must be patient. But when an event like a supernova does occur, the rewards are immense. We gain insight into processes that occur nowhere else, under conditions that cannot be replicated in any laboratory on Earth. Let us now turn our attention to the broader context of Stephenson 218 within the galaxy and the universe. This star is located in the Stephenson 2 cluster, a young massive cluster in the constellation Scutum, relatively close to the galactic plane. The cluster is part of the Milky Way, our home galaxy, a barred spiral galaxy containing hundreds of billions of stars. The Milky Way is vast, about 100,000 light years across, and the Sun sits about 26,000 light years from the galactic center, in one of the spiral arms. Stephenson 218, at 19,000 light years from us, is actually closer to the galactic center than we are. It is located in a region of the galaxy that is rich in gas and dust, a region where star formation is active and where massive stars are more common. The galactic plane, where most of the galaxy's stars and gas reside, is a crowded and dynamic place, with stars being born and dying in a continuous cycle. The fact that Stephenson 218 is part of a cluster is also significant. Star clusters are groups of stars that form together from the same cloud of gas and dust. They are bound together by gravity, though the binding is often weak, and many clusters eventually disperse as their member stars drift apart. Open clusters, like Stephenson 2, are relatively young and contain a few dozen to a few thousand stars. Globular clusters, by contrast, are much older and contain hundreds of thousands of stars in a tightly bound sphere. Stephenson 2 is a massive open cluster, meaning it contains a relatively large number of stars and a significant number of massive stars. This makes it a prime target for studying massive star evolution, because it provides a sample of stars that all have the same age and initial composition, but different masses. By studying the cluster as a whole, astronomers can see how stars of different masses evolve and compare their properties at the same stage of life. The cluster's age is estimated to be around 14 to 20 million years, which is young by cosmic standards. Most of the stars in the cluster are still on the main sequence, burning hydrogen in their cores. But the most massive stars have already evolved off the main sequence and become red supergiants. Stephenson 218 is one of these evolved stars, and it is likely the most massive, or one of the most massive members of the cluster. Its size and luminosity mark it as an outlier, a star that has reached an extreme stage of evolution. The presence of multiple red supergiants in the Stephenson 2 cluster is also noteworthy. In addition to Stephenson 218, the cluster contains several other red supergiants of comparable size and luminosity. This is unusual. Red supergiants are rare, and finding several of them in the same cluster is a stroke of astronomical luck. It suggests that the cluster had a population of very massive stars to begin with, and that several of them have now reached the red supergiant phase at roughly the same time. This clustering of extreme stars provides a unique opportunity for comparative studies. Astronomers can observe multiple red supergiants with similar ages and compositions and see how they differ. Are they all the same size, or do they vary? Do they all have the same mass loss rates, or are there differences? By answering these questions, astronomers can learn more about the factors that control the evolution of massive stars. One intriguing possibility is that some of these stars may interact with each other. In dense stellar environments, stars can pass close to one another, and in rare cases, they can even collide or merge. While Stephenson 2 is not as dense as a globular cluster, it is still possible that some of its stars have undergone interactions. If two massive stars merge, the result could be an even more massive star, one that might evolve into a red supergiant of exceptional size. This is speculative, but it is one of the hypotheses that astronomers consider when trying to explain the existence of the largest stars. Another factor to consider is the initial composition of the stars. Stars are made primarily of hydrogen and helium, but they also contain small amounts of heavier elements, collectively known as metals in astronomical parlance. The fraction of metals in a star affects its opacity, its ability to absorb and emit radiation, and this in turn affects its structure and evolution. Stars with higher metallicity tend to have stronger stellar winds and may lose mass more rapidly. They may also evolve differently, with changes in the size and duration of various evolutionary phases. The Stephenson 2 cluster is located in a region of the galaxy with relatively high metallicity, meaning the stars contain more heavy elements than stars in some other regions. This could influence the evolution of its member stars, potentially contributing to the large sizes of its red supergiants. By comparing stars in Stephenson 2 to red supergiants in other clusters or regions with different metallicities, astronomers can test this hypothesis and learn more about how composition affects stellar evolution. The study of stars like Stephenson 2-18 also connects to broader questions about the life cycle of matter in the universe. Stars are not isolated objects. They are part of a larger ecosystem, the interstellar medium, a vast expanse of gas and dust that fills the space between stars. This medium is the raw material from which stars form, and it is also the repository for the material that stars eject when they die. When a massive star like Stephenson 2-18 explodes as a supernova, it returns most of its mass to the interstellar medium. This material is enriched with heavy elements created in the star's core and in the explosion itself. Over time, this enriched gas mixes with the existing interstellar medium, raising its metallicity. Eventually, new stars form from this enriched gas, and they incorporate the heavy elements into their structure. Planets that form around these stars also contain heavy elements, including the carbon, oxygen, and iron that are essential for life. This process of stellar birth, life, and death, repeated over billions of years, is how the universe has gradually become enriched with heavy elements. In the early universe, shortly after the Big Bang, there were no heavy elements at all, only hydrogen and helium. The first stars, known as population Earth stars, were made entirely of primordial material. When these stars died, they created the first heavy elements, which were incorporated into the next generation of stars, known as population 2e. Our Sun is a population I star, formed from material that has been cycled through multiple generations of stars and is relatively rich in heavy elements. Stephenson 2-18, as a massive star that will soon explode, is part of this ongoing cycle. It is an agent of chemical evolution, a star that will contribute to the enrichment of the galaxy and help pave the way for future generations of stars and planets. In this sense, it is not just an object of curiosity, but a participant in one of the grand processes that shape the universe. There is also a philosophical dimension to contemplating stars like Stephenson 2-18. The sheer scale of the star forces us to confront the limits of human experience and understanding. We live on a small planet orbiting an ordinary star in an unremarkable part of the galaxy. Our entire existence, all of human history, all of our achievements and struggles, take place on a tiny stage that is utterly insignificant compared to the vastness of the cosmos. Stephenson 2-18, a single star among hundreds of billions in our galaxy alone, is so large that it could swallow our entire solar system. It is a reminder of how small we are, how limited our perspective is, and how much there is in the universe that lies beyond our direct experience. And yet we can understand this star through the application of physics and mathematics, through careful observation and rigorous analysis. We can determine its properties, trace its evolution, and predict its fate. This is one of the great triumphs of science. We may be small, but our minds are not limited by our physical size. We can reach out across the light years, study objects we will never visit, and comprehend phenomena that occur on scales far beyond our everyday experience. This ability to understand the universe, to uncover its secrets and make sense of its workings, is perhaps the most remarkable thing about our species. Stephenson 218 also raises questions about the existence of even more extreme objects. Is this star truly the largest, or might there be even larger stars waiting to be discovered? The universe is vast, and we have surveyed only a fraction of it. There may be stars in distant galaxies, or in obscured regions of our own galaxy, that are even larger than Stephenson 218, or there may not. It is possible that we have already found the most extreme examples, the stars that sit at the absolute limit of what is physically possible. Theoretical models suggest that there is indeed a maximum size for stars, and that this maximum is not much larger than the size of Stephenson 218. Stars much larger than this would be so unstable that they could not hold themselves together. Their radiation pressure would be too strong, their surface gravity too weak, and they would simply blow themselves apart. So it is likely that Stephenson 218 is close to the upper limit, if not at it. But nature has a way of surprising us. There may be loopholes, rare conditions under which a star could grow even larger, at least temporarily. There may be transient states, brief moments in a star's evolution when it swells to even more enormous proportions before collapsing or exploding. These possibilities are the subject of ongoing research, and future observations may yet reveal new surprises. For now, Stephenson 218 stands as one of the titans of the galaxy, a star of almost unimaginable size and power. It is a monument to the extremes of nature, a testament to the fact that the universe can create objects that challenge our understanding and stretch the limits of what is possible. Let us also consider the technology and ingenuity required to discover and study a star like this. 19,000 light years is an immense distance, far beyond the reach of any spacecraft we could build with current technology. Even traveling at the speed of light, it would take 19,000 years to get there, and our fastest spacecraft move at a tiny fraction of the speed of light. Voyager 1, the most distant human-made object, has been traveling for over 4 decades and has covered only a tiny fraction of a light year. At its current speed, it would take tens of thousands of years to reach even the nearest stars, let alone Stephenson 218. So we cannot go there. We cannot visit this star, land on its surface, or send a probe to study it up close. All we can do is observe it from a distance, collecting the light that has traveled across the galaxy to reach us. And yet, from this light alone, we can learn an astonishing amount. We can determine the star's temperature, its composition, its luminosity, its size, and even its internal structure. We can trace its history and predict its future. This is the power of spectroscopy, the analysis of light, one of the most important tools in the astronomer's toolkit. When light from a star passes through a prism or a diffraction grating, it is spread out into a spectrum, a rainbow of colors. But if you look closely at this spectrum, you see that it is not a smooth gradient. It is crossed by dark lines, absorption lines, where certain colors are missing. These lines are the fingerprints of the elements in the star's atmosphere. Each element absorbs light at specific wavelengths, creating a unique pattern of lines. By identifying these lines, astronomers can determine what elements are present in the star and in what amounts, but the spectrum reveals much more than just composition. The overall shape of the spectrum, the distribution of intensity across different wavelengths, tells us the star's temperature. Hotter stars emit more light at shorter wavelengths, appearing blue or white, while cooler stars emit more light at longer wavelengths, appearing red. By fitting the spectrum to a theoretical model, astronomers can determine the star's surface temperature with precision. The width of the spectral lines also carries information. If the star is rotating, or if its surface is turbulent, the light from different parts of the star will be Doppler, shifted by different amounts, causing the lines to broaden. By measuring this broadening, astronomers can infer the star's rotation speed and the degree of turbulence in its atmosphere. And if the star is part of a binary system orbiting another star, The Doppler shift will vary over time as the star moves toward and away from us in its orbit. By measuring these variations, astronomers can determine the orbital parameters and, in favorable cases, the masses of the stars involved. All of this information and more is encoded in the light. It is a treasure trove of data waiting to be decoded by those who know how to read it, and the techniques for reading it have been refined over more than a century of careful work by generations of astronomers. The study of Stephenson 218 has benefited from advances in technology as well. Modern infrared telescopes, both on the ground and in space, have been crucial for observing this star through the intervening dust. Instruments like the Spitzer Space Telescope and the Herschel Space Observatory have provided detailed infrared spectra and images, allowing astronomers to study the star and its circumstellar environment in unprecedented detail. Ground-based telescopes equipped with adaptive optics, which correct for the blurring effects of Earth's atmosphere, have also contributed to our understanding. As technology continues to advance, we can expect even better observations in the future. The James Webb Space Telescope, with its powerful infrared capabilities, is already providing new insights into stars and star-forming regions across the universe. Future missions and telescopes will push the boundaries even further, allowing us to study stars like Stephenson 218 with greater precision and to discover new examples of extreme stellar objects. There is also the question of how we communicate the scale of these objects to a general audience. As scientists, we are comfortable working with numbers like 2,000 solar radii or 10 billion cubic kilometers, but these numbers are abstract and difficult to visualize. How do we convey the true scale of Stephenson 218 to someone without a background in astronomy? One approach is to use comparisons, as we have been doing throughout this discussion. Comparing the star to familiar objects, like the sun or the planets, helps ground the numbers in something tangible. Describing how long it takes light to cross the star, or how many Earths could fit inside it, provides a sense of scale that pure numbers cannot. Another approach is to use visual representations. Imagine a diagram showing the sun at the center, with the orbits of the planets drawn around it, and then a circle representing Stephenson 218 superimposed on top, dwarfing everything. Such a diagram makes the comparison immediate and visceral. You do not need to do any mental math. You can see at a glance how much larger the star is. Videos and animations can be even more effective. Imagine an animation that starts with a view of Earth, then zooms out to show the Earth-Moon system, then the inner solar system, then the entire solar system, and finally the size of Stephenson 218 superimposed on top. The progressive zooming helps convey the nested scales, each one larger than the last, until we reach the final, almost incomprehensible size of the star. These communication tools are important because they help make astronomy accessible. The universe is full of wonders, but if we cannot convey those wonders to people in a way that is understandable and engaging, then we lose the opportunity to share the excitement of discovery and the beauty of the cosmos. Astronomy, at its best, is not just about data and equations. It is about awe and wonder, about the realization that we live in a universe far stranger and more magnificent than we ever imagined. Stephenson 218 embodies this sense of wonder. It is a star that defies easy comprehension, that forces us to expand our sense of what is possible. And it is real. It is not a thought experiment or a mathematical curiosity. It is an actual object, made of matter, obeying the laws of physics, existing in our galaxy at this very moment. We should also reflect on the fact that our knowledge of this star, and of the universe in general, is the product of cumulative effort over many generations. No single person discovered Stephenson 218 or figured out all of its properties. Instead, it is the result of a long chain of contributions from the astronomers who first catalogued the stars in this region of the sky, to those who studied the cluster and identified its red supergiants, to those who made the detailed measurements and calculations needed to determine the star's size. Each person built on the work of those who came before, adding a piece to the puzzle, refining the picture, pushing our understanding a little further. This collaborative, cumulative nature of science is one of its great strengths. It means that our knowledge is robust, based on multiple independent lines of evidence, and verified by many different people. It also means that science is a fundamentally human endeavor, a collective effort to understand the world around us. And yet, despite all we have learned, there is still so much we do not know. The universe is vast and complex, and we have barely scratched the surface. For every question we answer, we uncover new questions. For every mystery we solve, we find new mysteries. This is not a failing of science. It is a feature. It is what keeps the field vibrant and exciting, and it is what ensures that there will always be new discoveries to make, new frontiers to explore. Stephenson 218 is a perfect example of this. We have learned a great deal about this star, but there is still much we do not understand. We do not know its exact mass or age. We do not know the precise details of its internal structure or the mechanisms driving its mass loss. We do not know when it will explode or exactly what the supernova will look like. These are questions that future observations and improved models will help answer. And there are broader questions as well. How common are stars like Stephenson 218? Are they rare outliers, or are there many such stars scattered throughout the galaxy, waiting to be discovered? What role do they play in the chemical evolution of the galaxy? How do their supernovae differ from those of other types of massive stars? These are questions that connect to our understanding of the galaxy as a whole and the processes that govern its evolution. Let us now think about the energy output of this star. Luminosity, the total amount of energy a star emits per second, is one of the key properties that defines a star. The Sun has a luminosity of about 3.8 times 10 to the 26th watts. This is an enormous amount of energy, equivalent to detonating about 90 billion megatons of TNT every second. And yet, compared to Stephenson 218, the Sun is a dim ember. Estimates of Stephenson 218's luminosity vary, but it is likely somewhere around 400,000 times the luminosity of the Sun. 400,000. This means that every second, Stephenson 218 emits as much energy as the Sun does in more than 4 days. The star is a titanic engine, converting mass into energy through nuclear fusion at a rate that is almost beyond comprehension. Where does all this energy go? Most of it radiates away into space as light, primarily in the infrared due to the star's cool surface temperature. Some of it is carried away by the stellar wind, the stream of particles that flows outward from the star, and some of it is absorbed by the surrounding circumstellar material, heating the dust and gas and causing it to glow. The energy output of Stephenson 218 also has implications for its lifetime. Stars are powered by nuclear fusion, and the total amount of energy a star can produce is determined by how much fuel it has and how efficiently it can fuse that fuel. Massive stars have more fuel than low-mass stars, but they also burn it much more quickly. A star with 10 times the mass of the Sun has 10 times as much fuel, but it burns it at a rate thousands of times faster, so its lifetime is much shorter. Stephenson 218, despite its enormous size, has a relatively modest mass compared to the most massive stars, but it is still far more massive than the Sun, and it is in a late stage of evolution, burning through its remaining fuel at a furious pace. The star's lifetime as a red supergiant is measured in thousands or tens of thousands of years, a fleeting moment in cosmic terms, and when the fuel runs out, the star will collapse and explode, ending its life in a blaze of glory. This brings us back to the question of why stars like Stephenson 218 cannot last. The problem is that as the star evolves, it becomes increasingly unstable. The core contracts and heats up, fusing heavier and heavier elements, while the outer envelope expands to ever more enormous sizes. The envelope becomes so diffuse and so loosely bound that it is barely held in place by gravity. The radiation pressure from the core, combined with pulsations and other instabilities, drives mass loss at an accelerating rate. The star is literally tearing itself apart. There is also a thermodynamic issue. Stars are heat engines, and like all heat engines, they are subject to the laws of thermodynamics. The energy produced in the core must be transported to the surface and radiated away. In a stable star, this transport is efficient, and the star maintains a steady state. But in a red supergiant, the envelope is so large and so diffused that energy transport becomes problematic. The star develops convective zones, regions where heat is carried by bulk motion of material rather than by radiation. These convective zones can be turbulent and chaotic, leading to fluctuations in the star's luminosity and size. All of this adds up to a star that is on the edge of instability, a star that cannot maintain its structure indefinitely. Stephenson 218 is living on borrowed time, and its fate is sealed. It will explode, and when it does, it will leave behind a legacy in the form of a neutron star or black hole and a cloud of enriched material that will seed the next generation of stars. But let us not dwell only on the star's death. Let us also appreciate its existence. For as long as it shines, Stephenson 218 is a marvel, a testament to the power of nature to create objects of staggering scale and complexity. It is a star that challenges our intuitions, expands our horizons, and reminds us of the incredible diversity of the cosmos. Consider also the journey that light from this star has taken to reach us. 19,000 years ago, when the light we see today left Stephenson 218, humans on Earth were emerging from the last ice age. The climate was warming, glaciers were retreating, and early humans were beginning to settle in new regions, developing agriculture and building the first permanent settlements. Over the millennia that followed, civilizations rose and fell, writing was invented, cities were built, empires expanded and collapsed. Art, science, philosophy, all the achievements of human culture developed over this span of time. And throughout all of this, light from Stephenson 218 was traveling through space, crossing the vast distances of the galaxy, passing through clouds of gas and dust, unaffected by the events unfolding on a small planet orbiting an unremarkable star. Finally, after 19,000 years, that light reached Earth. Some of it entered our telescopes, was focused onto detectors, and was converted into data that astronomers could analyze. And from that data, we learned about the star, about its size and temperature and luminosity, about its place in the galaxy and its role in the cosmic story. This is a profound connection, a link across space and time that binds us to distant objects and events. Every photon we collect from Stephenson 218 is a messenger from the past, a tangible link to a star that existed long before recorded history. And when we study these photons, we are not just learning about the star, we are also learning about the universe itself, about the laws of physics that govern it, about the processes that shape it, and about our place within it. There is also something humbling about this. We are a young species, living on a young planet, orbiting a middle-aged star, in a galaxy that is itself billions of years old. The light we see from Stephenson 218 began its journey when our species was in its infancy, when we were just beginning to develop the traits and capabilities that would eventually lead to civilization. In the grand scheme of things, we have only just arrived on the cosmic stage, and yet we have already learned so much. We have mapped the stars, measured their distances, determined their properties, and begun to understand their life cycles. This is an extraordinary achievement, and it speaks to the power of human curiosity and ingenuity. But it also reminds us of how much there is still to learn. The universe is not static. It is evolving, changing, with stars being born and dying, galaxies colliding and merging, and new structures forming on the largest scales. Every observation we make is a snapshot, a single frame in a vast and ongoing story. To truly understand the universe, we need to observe it over time, to watch how it changes, and to see the processes that drive that change. This is one of the great challenges of astronomy. The timescales of cosmic evolution are so long that we cannot see most changes happen in real time. A star like Stephenson 218 may take thousands of years to evolve from one stage to the next, far longer than a human lifetime. We cannot watch a single star go through its entire life cycle. Instead, we must observe many stars at different stages and piece together the story from these snapshots. This is where stellar populations and clusters like Stephenson 2 become invaluable. By studying a cluster, we can see stars of different masses at different stages of evolution, all with the same age and initial composition. This allows us to test our models of stellar evolution and to fill in the gaps in our understanding. It is like studying a forest to understand the life cycle of trees. We cannot watch a single tree grow from seed to maturity to death, but we can observe many trees at different stages and infer the pattern. The study of stars like Stephenson 218 also intersects with other areas of astrophysics. For example, these stars are sources of heavy elements, and the supernova they produce are among the most energetic events in the universe. Supernova explosions can trigger the formation of new stars by compressing nearby gas clouds, and they can also inject energy into the interstellar medium, heating it and driving galactic winds. These processes play a key role in regulating star formation and shaping the structure of galaxies. Massive stars like Stephenson 218 are also thought to be important sources of cosmic rays, high-energy particles that permeate the galaxy. When a star explodes as a supernova, the shock wave accelerates particles to near the speed of light, and these particles can travel across the galaxy, carrying energy and affecting the chemistry and physics of the interstellar medium. Some of these cosmic rays eventually reach Earth, where they can be detected by instruments on the ground and in space. There are also connections to the study of exoplanets and the search for life. While it is unlikely that planets could survive the red supergiant phase of a star's evolution, the heavy elements produced by stars like Stephenson 218 are essential for planet formation. Rocky planets like Earth are made of elements like silicon, iron, and oxygen, all of which are produced in the cores of massive stars and dispersed by supernovae. Without the contributions of past generations of massive stars, there would be no planets and no life. In this sense, Stephenson 218 is part of the larger story of cosmic evolution, the process by which the universe has gradually become more complex and diverse over time. From the simple hydrogen and helium of the early universe, we have arrived at a cosmos rich in structure, from galaxies and stars to planets and, on at least one planet, life. This evolution is driven by the life cycles of stars, by the processes of fusion and explosion that create new elements and disperse them into space. Let us also consider the observational challenges involved in studying Stephenson 218. The star is located near the galactic plane, in a region of the sky that is crowded with stars and obscured by dust. This makes it difficult to isolate the star and measure its properties with precision. The dust absorbs and scatters light, particularly at shorter wavelengths, making the star appear dimmer and redder than it would otherwise. To correct for this, astronomers must estimate the amount of dust along the line of sight, which is not always straightforward. Infrared observations help, but they introduce their own challenges. Infrared light is affected by Earth's atmosphere, which absorbs and emits infrared radiation, creating a bright and variable background that can interfere with observations. This is why many infrared telescopes are placed in space, above the atmosphere, where they can observe without this interference. But space telescopes are expensive and limited in number, so ground-based observations are still important. Advances in technology, such as adaptive optics and better infrared detectors, have made ground-based infrared astronomy increasingly powerful. Another challenge is the star's variability. Red supergiants like Stephenson 218 are known to vary in brightness over time, sometimes by a significant amount. This variability is caused by pulsations and other changes in the star's atmosphere. To get an accurate picture of the star's properties, astronomers need to observe it multiple times and average out these variations. This requires long-term monitoring campaigns, which can span months or years. There is also the challenge of distinguishing Stephenson 218 from other stars in the cluster. The cluster is rich in red supergiants, and they can appear close together on the sky. High-resolution imaging is needed to separate them and measure each star individually. This is where large telescopes with excellent resolving power become essential. Despite these challenges, astronomers have made remarkable progress in studying Stephenson 218 and other extreme stars. Each new observation adds to our knowledge, refining our estimates of the star's properties and improving our understanding of its nature. And as technology continues to advance, we can expect even more detailed and accurate observations in the future. The study of Stephenson 218 also highlights the importance of international collaboration in astronomy. No single telescope or observatory can provide all the data needed to fully understand this star. Instead, astronomers rely on a network of facilities around the world, each contributing different types of observations. Some telescopes are better suited for infrared observations, others for optical or ultraviolet. Some are located in the northern hemisphere, others in the southern hemisphere, allowing continuous coverage of the sky. By combining data from multiple sources, astronomers can build a more complete picture. This collaborative approach extends beyond individual observatories to include entire research communities. Astronomers share their data, publish their findings, and build on each other's work. This open and collaborative culture is one of the strengths of science, and it is what allows progress to be made even on the most challenging problems. Let us now return to the question of what makes Stephenson 218 special. In a galaxy of hundreds of billions of stars, why does this one matter? The answer is that it represents an extreme, a boundary case that tests our understanding of stellar physics. By studying objects at the extremes, we learn about the limits of what is possible and the processes that set those limits. Stephenson 218 is not just large. It is about as large as a star can be. It sits at the edge of a cliff, beyond which stars cannot exist. This makes it scientifically valuable. It is a natural laboratory for studying the interplay of gravity, radiation, and matter under extreme conditions. It allows us to test our models of stellar structure and evolution in a regime that is difficult to access through theory alone, and it provides a glimpse into the final stages of massive star evolution, the processes that lead up to a supernova. But beyond its scientific value, Stephenson 218 also has a kind of aesthetic appeal. There is something awe-inspiring about an object of such immense scale, something that speaks to our sense of wonder and curiosity. It is a reminder that the universe is full of marvels, that there are objects and phenomena out there that surpass our wildest imaginings. And it is a testament to the power of human intellect, to our ability to study and understand things that are so far removed from our everyday experience. In many ways, Stephenson 218 is emblematic of the entire field of astronomy. Astronomy is the study of things we cannot touch, cannot visit, and in many cases, cannot even see directly. It is a science built on inference, on the analysis of light and the application of physical laws. And yet, through this indirect approach, we have learned an astonishing amount. We have mapped the cosmos, measured the distances to galaxies billions of light years away, determined the age of the universe, and traced its evolution from the Big Bang to the present day. We have discovered thousands of planets orbiting other stars, detected gravitational waves from colliding black holes, and imaged the shadow of a supermassive black hole at the center of a galaxy. All of this is possible because of the scientific method, the systematic approach to understanding the natural world through observation, experimentation, and reason. And all of it is driven by curiosity, by the desire to know, to understand, to make sense of the universe we inhabit. Stephenson 218 is a product of this curiosity. It was discovered because astronomers wanted to know what was out there, what kinds of stars existed, and how large they could be. It was studied because astronomers wanted to understand its properties, to fit it into the larger picture of stellar evolution, and to learn what it could teach us about the universe. And it will continue to be studied because there is always more to learn, always new questions to ask, always deeper insights to gain. As we approach the end of this exploration, it is worth reflecting on the broader implications of what we have discussed. Stephenson 218 is a single star, one object among countless others in the universe. And yet, in studying this one star, we have touched on some of the deepest questions in astronomy and physics. We have explored the nature of matter and energy, the limits of physical law, the life cycles of stars, and the evolution of the universe. We have seen how a single object can illuminate broader truths, and how the study of the specific can lead to understanding of the general. This is the power of science. It allows us to take the particular and extract the universal, to see patterns and connections, and to build models that explain not just one phenomenon, but many. And it allows us to make predictions, to anticipate what we will find when we look in new places or observe in new ways. But science is also humble. It recognizes its own limitations, acknowledges uncertainty, and is willing to revise its conclusions in light of new evidence. Our understanding of Stephenson 218 is not final. It is provisional, subject to change as we gather more data and develop better models. This is not a weakness. It is a strength. It means that science is self-correcting, that it improves over time, and that it moves ever closer to the truth. We should also remember that the universe does not exist for our benefit. It is not designed to be comprehensible or to make sense to us. The fact that we can understand it at all is remarkable, a testament to the power of reason and the consistency of natural law. But there may be aspects of the universe that are beyond our current understanding, questions we cannot yet answer, and perhaps even questions we have not yet thought to ask. Stephenson 218, in all its immense glory, is just one small piece of a much larger puzzle. The universe is vast and complex, filled with objects and phenomena that span an incredible range of scales, from the subatomic to the cosmic. Each piece of this puzzle is connected to the others, part of a grand tapestry that we are only beginning to perceive. As we look to the future, we can anticipate new discoveries and new insights. Future telescopes will allow us to observe stars like Stephenson 2-18 in greater detail, to study their atmospheres, to track their pulsations, and to monitor their evolution in real time. New theoretical models will incorporate more physics, more complexity, and more realism, allowing us to make more accurate predictions. And new technologies, from machine learning to quantum computing, may open up entirely new ways of analyzing data and extracting information. But no matter how much we learn, there will always be more to discover. The universe is too large, too complex, and too rich in detail for us to ever fully comprehend it. And that is as it should be. The sense of wonder, the feeling of awe in the face of the unknown, is part of what drives us to explore, to question, and to seek understanding. It is what makes us human. Stephenson 218 stands as a monument to this quest for understanding. It is a star that pushes the boundaries of what is possible, that challenges our assumptions, and that invites us to think bigger, to imagine more, and to never stop asking questions. It is a reminder that the universe is full of wonders, and that we are privileged to live in a time when we have the tools and the knowledge to study them. In the end, Stephenson 218 is not just a star, it is a symbol of the human spirit, of our desire to explore and understand, of our capacity for reason, and our willingness to confront the unknown. It is a testament to the power of science and the beauty of the cosmos, and it is a reminder that, no matter how small we are in the grand scheme of things, we are capable of great things, of understanding the universe and our place within it. As this star continues to shine, burning through its final reserves of fuel, it serves as a beacon, a light in the darkness, guiding us on our journey of discovery. And when it finally explodes, when it ends its life in a supernova that will briefly outshine an entire galaxy, it will leave behind a legacy, a cloud of enriched material that will seed the next generation of stars and planets, and perhaps one day, new life. This is the cycle of the cosmos, the endless dance of creation and destruction, of birth and death, of matter and energy transforming and recombining in an ever-changing pattern. We are part of this cycle, made of the same elements, governed by the same laws, connected to the stars in ways both literal and profound. Stephenson 218 reminds us of this connection. It reminds us that we are not separate from the universe, but part of it, participants in its grand story. And it reminds us that the universe is not a cold, lifeless void, but a dynamic, evolving, and ultimately comprehensible place, full of beauty, wonder, and mystery. In contemplating this star, we are doing more than just studying an astronomical object. We are engaging in an act of profound significance, reaching out across the vastness of space and time to touch something that is both utterly alien and intimately connected to us. We are exercising our greatest gift, the gift of reason, the ability to observe, to think, to question, and to understand. And in doing so, we are fulfilling a fundamental aspect of what it means to be human. We are explorers, seekers of knowledge, driven by an insatiable curiosity about the world around us. From our earliest ancestors who looked up at the night sky and wondered what the stars were, to the modern astronomers who use sophisticated instruments to probe the depths of space, we have always been driven by the desire to know, to understand, to make sense of the cosmos. Stephenson 218 is part of this ongoing quest. It is one more piece of the puzzle, one more clue in our attempt to understand the universe. And while we may never fully comprehend all its mysteries, the journey itself is worthwhile, the pursuit of knowledge its own reward. So as we conclude this exploration, let us take a moment to appreciate what we have learned. We have journeyed to one of the most extreme objects in the galaxy, a star so large that it defies easy comprehension. We have explored its properties, its structure, its evolution, and its place in the cosmic story. We have seen how it connects to broader questions in astronomy and physics, and we have reflected on what it means for our understanding of the universe and our place within it. Stephenson 218 is a marvel, a testament to the power of nature and the ingenuity of humanity. It is a star that sits at the very edge of what is possible, a monument to cosmic extremity. And it is a reminder that the universe is capable of creating things that are far stranger, far more magnificent, and far more wondrous than we ever imagined. As we turn our gaze back to our own small world, back to the everyday concerns and challenges of human existence, let us carry with us the perspective that Stephenson 2:18 provides. Let us remember that we live in a universe of staggering scale and complexity, a universe that is both humbling and inspiring. Let us remember that we are part of something much larger than ourselves, connected to the stars and to the cosmos in ways both tangible and mysterious. And let us remember that the pursuit of knowledge, the quest to understand the universe, is one of humanity's noblest endeavors. It is what sets us apart, what makes us special, what gives meaning and purpose to our existence. In studying the stars, we are not just learning about distant objects. We are learning about ourselves, about our origins, about our place in the grand scheme of things. Stephenson 2:18 shines in the darkness, a giant among giants, a star at the very limits of existence. It burns with a fury that dwarfs our sun, illuminating a small corner of the galaxy, and in doing so, it illuminates our understanding as well. It teaches us about the nature of stars, about the forces that govern them, and about the boundaries beyond which they cannot go. And one day, perhaps thousands of years from now, perhaps tomorrow, this star will reach the end of its life. It will collapse and explode, and for a brief moment, it will shine brighter than anything else in the sky. And we, if we are watching, if we are still here, will witness that explosion, study it, learn from it, and add another chapter to the story of the cosmos. But for now, Stephenson 2:18 endures, a quiet giant in the depths of space, waiting, burning, existing at the very edge of what the universe allows. It is a star that reminds us of how vast the cosmos is, how small we are, and yet how remarkable it is that we, tiny creatures on a tiny planet, can reach out across the light years and understand something so immense, so distant, and so utterly beyond the scale of our everyday lives.